give it a moment for YouTube to start. Waiting for Kaggle. Oh, excellent. All right, looks like we're live. Hopefully people who are watching on YouTube can hear okay. We are broadcasting from Kaggle Days in San Francisco. And I know there's no video feed, but I promise you that there's like 10 people in the room taking a break from the competition. Thank you. So if you're in the room and you have questions or comments, feel free to holler and I will repeat them into my high quality headphone microphone. It's not very high quality. Make sure everyone can join in. Hi, Jer. Good to see you, Jer on YouTube. So today we're going to be reading one of the best papers from NACL, which is the North American Association for Computational Linguistics conference. It's one of the big NLP conferences. And they just announced their best papers. And this was a short paper, so I think we can get through it in an hour, but we will find out. And it is on multimodal machine translation, which is not something I've looked into a whole lot. I'm sort of familiar with machine translation in general, but this one in particular is, one sec, there we go. This one in particular, sorry, I just realized I was showing the people in the room, not the big version of the paper. Integrating image data and text data for machine translation, so from one language to another language automatically. Let's just kick off. So current work in multimodal machine translation, MMT, and I'm sure they will use that acronym throughout, has suggested that the visual modality is either unnecessary or only marginally beneficial. So basically, we are ignoring the pictures for MMT, or when they try to use them, they're not getting a lot of benefit from them. The authors continue, we posit that this is a consequence of the very simple, short, and repetitive sentences used in the only available data set from the task, Multi-30K, which I'm not super familiar with. Let's actually take a quick peek and see if we can see what some of those data sets look like, some of the training examples. So it looks like it's on GitHub. And they have pre-extracted visual features, but they don't have the raw images, which is probably due to licensing, because image licensing tends to be a little bit trickier than code licensing. And you generally have to license each individual image separately, which is a bit of a pain. And they have 29,000 sentences, 377,000 words, so like 10-ish words per sentence, which is pretty short. And then it's English, German, French, and CS, Czech maybe? Anyone know the IS code for CS, what that is? English and German, French, ambiguous, Czech. It is Czech, okay. And this was at Proceedings of the Third Conference on Machine Translation in 2018. So it's a fairly recent data set. So images with extracted features and short sentences. Rendering the source text sufficient as context. So they're saying that previous work using these pre-extracted features and these sentences has found that the images aren't as helpful. Or maybe the pre-extracted features, maybe if you're working on the full images, you'll get better results. In the general case, however, we believe that it is possible to combine visual and textual information in order to ground translations. So looking at the pictures and getting information from them. In this picture, we probe the contribution of the visual modality to state-of-the-art MMT models by conducting a systematic analysis where we partially deprive the models from source-side textual context. Okay, so it looks like they're doing sort of ablation experiments, but on the data. So they are removing some of the text and then seeing what information they can get from the images. Our results show that under limited textual context, models are capable of leveraging the visual input to generate better translations. So when you have degraded information from the text, you can use the image to get better translations. This contradicts the current belief that MMT models disregard the visual modality because of either the quality of the image features or the way they are integrated into the model. Okay, so at first blush, this makes a lot of sense to me. Just if you have pictures and you can get good information from pictures, it's helpful. And if you're only relying on text, you might do a little bit worse. And then it seems to be particularly helpful in the case where you have degraded textual information. Something that might be relevant here is that there's a recent study, and I don't remember who it was by, looking at bias in the text of captions. And they found that you tend to have a lot of adjectives, you tend to have a lot of nouns, but you don't have a lot of verbs. So verbal information like running, skipping, hopping, jumping, that sort of thing isn't overrepresented in captions. And it also seems like that, I'm not a vision person, it seems like that would be harder to get from vision. So maybe because we're focusing on nouns and adjectives, that's part of the reason why images can be helpful. All right, let's hop in. Introduction. Multimodal machine translation aims at designing better translation systems which take into account auxiliary inputs such as images. The thing that I'm most familiar with that's most related is automatic image captioning, so generating descriptions of images while they're running, especially for video. But this has the additional wrinkle of you're also doing translation at the same time. Initially organized as a shared task within the first conference on machine translation, WMT 16, which I think is an ACL conference, Specia et al. 2016. MMT has so far been studied using the Multi-30K dataset, a multilingual extension of the Flickr 30K with translations of the English image descriptions into German, French, and Czech. Okay, so these are user-generated descriptions, it looks like, and not like a mturk or tagging task. It looks like these are naturally occurring data, if you will. The 3 editions of the shared task have seen many exciting approaches that can be broadly categorized as follows. 1, multimodal attention using convolutional features. So I'm guessing that this is maybe in the encoder step. You're including attention, but you're taking those attention features from the images and not just from the text data, is my guess, based on reading one sentence. 2, cross-modal interactions with spatially unaware global features. Cross-modal interactions. Spatially unaware global features. So spatially is like space. So they're not looking at space and they're just getting global features. So like how dark the image is? I don't know what that means. Let's continue on and see if they expand on it. And if anyone has more information, please feel free to chime in because I don't know what that is. And 3, the integration of regional features from object detection networks. Okay, that makes a lot of sense. So let's say you've got English or French and there's a picture of an apple and you identify the apple and you're like, oh, I know the word for apple, it's palm, and then you use that. So that's probably the approach that I personally would take as a naive person if I were approaching this problem. Nevertheless, the conclusion about the contribution of the visual modality is still unclear. Gronroos, looks like Dutch maybe, et al. 2018 consider the multimodal gains modest and attribute the largest gain to the use of external parallel corpora. Interesting. So I guess you're sort of using larger external corpora as a proxy for world knowledge. So you happen to know that apples and kitchens tend to go together and not necessarily have a bunch of pictures of apples and kitchens, is my take from that. The organizers of the latest edition of the... Nope, I skipped a sentence, sorry. Lala et al. 2018 observed that their multimodal word sense disambiguation approach is not significantly different than the monomodal counterpart. So including the images doesn't make a big difference. The organizers of the latest edition of the shared task conclude that the multimodal integration schemes explored so far resulted in marginal changes in terms of automatic metrics and human evaluation. In the same vein, Elliott 2018 demonstrated that MMT models can translate without significant performance loss, even in the presence of features from unrelated images. Interesting. So basically all of these studies are saying when we do image processing, when we add this step, actually it doesn't help that much. And that's important to consider because image processing tends to be very computationally expensive. You need to get the rights to the images, which can be expensive. And it just doesn't make that much difference. So people are sort of throwing away the image data. So that's sort of the state of the art so far. These empirical findings seem to indicate that images are ignored by the models and hint at the fact that this is due to representation or modeling limitations. So it's down to the way that they're processing the images and not the fact that images themselves aren't helpful. We conjecture that the most plausible reason for the linguistic dominance is that, at least in multi-30K, the source text is sufficient to perform the translation, eventually preventing the visual information from intervening in the learning process. Oh, and Andre on YouTube says, from Quora on global features. Oh, thank you. This is the one where I was like, I don't know what that is. Global features include contour representations, shape descriptors, and texture features, and the local features represent the texture in an image patch. Okay, so this would be sort of like what shapes there are, qualities of those shapes, and sort of the texture on the inside of the shape. So silhouettes, maybe? Although silhouette detection seems like it would be more object recognition. You can tell that I spent a lot of time working on computer vision, and it's definitely an area of my expertise. Thank you, Andre. That was very helpful. Where was I? So they're saying that the source text is sufficient. There's a lot of information in language. Getting more information out of the image isn't especially helpful, which is fairly counterintuitive to me. And it looks like there's a lot of results that demonstrate this that have already sort of been in the literature, and that there's a lot of parallel evidence. But I would think, again, as sort of a naive person, that images would be helpful. All right, so they are investigating this hypothesis. We introduce several input degradation regimes, section 2, and revisit state-of-the-art MMT models, section 3, to assess their behavior under degraded regimes. We further probe the visual sensitivity by deliberately feeding features from unrelated images. So if we're really not using information from an image, then having images that aren't related shouldn't help us. And if we actually are using that information, then this will hurt us. And then I guess we'll see what sort of input degradation they do. Our results, section 4, show that MMT models successfully exploit the visual modality when the linguistic context is scarce, but indeed tend to be less sensitive to this modality when exposed to complete sentences. Okay, so what I'm getting from this discussion, and obviously we haven't seen the results yet, is that they're saying that the information that you can get from images is more or less redundant to the information that's in the text descriptions, which makes sense, especially for user-generated for Flickr user-generated tags and descriptions, because at least when I'm writing image descriptions, I'm doing them as a caption for people who are visually impaired. So I want to make sure I get all the important information in the description. So I suppose that's not actually super surprising. I don't know. I could see this paper as being very surprising or very unsurprising, depending on your personal biases. All right, degradation. Input degradation. In this section, we propose several degradations to the input language modality to simulate conditions where sentences may miss crucial information. So maybe you have an adversarial example, or somebody's just really bad at writing captions. Or you might have lost part of it due to, I don't know, bad Wi-Fi connection or something. We denote a set of translation pairs by big D and indicate degraded variants with subscripts. That looks like a Latin letter I don't know. Greek letter, I don't know. Both the training and test sets are degraded. So the image degradation is removing color words and not color from the images. So we consistently replace source words that refer to colors with a special token V. So in machine translation, source is the language you're translating from, and target is the language you're translating to. So this is in the input language. D sub C in table 1. So an example would be a lady in a dress singing, where the missing token is blue. Entity masking. Oh, sorry, I didn't finish that thing. Our hypothesis is that a monomodal system will have to rely on source-side contextual information and biases, while a multimodal architecture could potentially capitalize on color information extracted by exploiting the image and thus obtain better performance. And Andre pointed out that color information, contour information, is in global features. So color information may or may not be in global features. This affects 3.3 to 3.1% of the words in the training and test set, respectively. 3% of the words are color descriptors. That's really high. I haven't said a color word in the last 15 minutes. My intuition for like the frequency and just sort of like conversational speech of colors in situations outside of maybe shopping for dresses is that it's like less than 1/3%. So that seems like perhaps there is some bias in image captioning specifically. All right, entity masking. The Flickr 30K dataset, from which the multi-30K is derived, not devolved, has also been extended with co-reference chains to tag mentions of visually depictable entities in image descriptions. We use these to mask out the head nouns in the source sentences. Okay, so things, I'm guessing these are concrete nouns like violin or cat or car. So things that you could show and not abstract concepts like freedom. And then they're removing the head nouns, so nouns that are the head of a noun phrase in the source sentence. And the example is D sub N, in a blue singing, where the missing words are lady and dress. This affects 26.2% of the words in both training and test set. That's reasonable. We tend to use a lot of nouns. We hypothesized that a multimodal system should heavily rely on the images to infer the missing parts. That makes sense to me. If you can figure out what's in the picture based on object detection, then you can probably figure out that someone would mention this in the caption if they are writing high-quality captions. Progressive masking. A progressively degraded variant D sub K replaces all but the first K tokens of the source sentence with V. So you get like the first half of the sentence, but not the second half of the sentence. Unlike the color deprivation and entity masking, masking out suffixes does not guarantee suffixes of the sentence, not suffixes at the token level, does not guarantee systematic removal of visual context, but rather simulates an increasingly low resource scenario. I don't know about that. I feel like people tend to still make full sentences, but just remove additional information. Maybe if you're pressed for time or you don't have a large vocabulary in the target language, but we'll see. Overall, we form 16 degraded variants T sub K, table 1, where K is in the set 0 through 30, hopping by 2, so 0, 2, 4, 6, etc., all the way to 30. We stop at D30 since 99.8% of the sentences in multi-30K are shorter than 30 words, with an average sentence length of 12 words. So by the time they get halfway through their degraded sense, we don't know what the average is. They should have reported median. Many sentences will be completely removed. D sub 0, where the only remaining information is the source sentence length. When is that ever going to occur in a machine translation setting? Is an interesting case from two perspectives. A neural machine translation model trained on it resembles a target language model. Yeah, okay, I get that. Well, an MMT model becomes an image captioner with access to expected length information. So they're saying if all you have is the information about how long the sentence is, you're not really doing machine translation anymore because you don't have the input sentence. You just have sort of like a picture and then how long a human wrote the caption as. These, I think, make a fair amount of sense. This is a weird way to do degradation. I probably would have, if I wanted to show increasingly missing information, I probably would have simplified the sentence structure. So I would have removed adjectives, adverbs, verbs, and then nouns in that order. Is probably how I would have done this. All right. Visual sensitivity. Inspired by Elliott, 2018. Andre says, They found a list on Wiki of global features, and that does include color. So we would expect color deprivation to, we would expect global features to give us some of the information that's missing when we remove color from the source sentence. Thank you, that was helpful. So I've got YouTube on a second screen here, and I'm just checking the comments. All right. Inspired by Elliott 2018, we experiment with incongruent decoding in order to understand how sensitive the multimodal systems are to visual modality. Incongruent decoding. So usually in most sequence-to-sequence tasks, you'll have an encoder and a decoder. And the encoder sort of takes the input sentence and transforms it to a vector of some sort, and then passes it to the decoder, and that takes that vector. And sometimes people refer to them as thought vectors, which I think is hooey, but and then translate that back into words. So incongruent decoding, I would imagine, is that they have a decoder that was trained on a different data set or for a different language? Question mark? This is achieved by explicitly violating the test time semantic congruence across modalities. Specifically, we feed the visual features in reverse sample order to break image sentence alignments. We feed the visual features in reverse sample order in order to break image sentence alignments. Okay, so this is at the level of the whole data set. So if we have n items in our data set, item 1 is going to have the image features from item n. Item 2 is going to have the image features from item n minus 1, and so on. So they've taken the features and they've reversed the whole vector across the data set, is what I'm getting from that. Consequently, a model capable of integrating the visual modality would likely deteriorate in terms of metrices. So we've got the features from the wrong image. So we are masking color information in the text. We're masking entities in the text. We're sort of chopping off the end of the sentence in progressively larger chunks. And we are changing the features so they're not the ones that were originally associated with the particular image that we're looking at. All right, experimental setup. We conducted experiments on the English to French part of multi-3K. Why just the English to French part? What about the rest of it? There's like 4 language pairs. Okay, so they did part of the data set. This strikes me as something that might have been, we had a conference deadline coming up and we needed to pick something that we could do in time. The models are trained on the concatenation of the train and val sets, so train and validation sets, 30 sentences, whereas test 2016 dev and test 2017 test are used for early stopping and model evaluation specifically. Okay, so they're actually using a total of 4 data sets, 4 subsections of the data set. They're using the training and the validation set from the first round to train. They're using the training data set from the second round for early stopping, and the testing data set from the second round for evaluation. For entity masking, we revert to the default Flickr 30K splits and perform the multiple evaluation on test 2016. Since test 2017 is not annotated for entities. Okay, I was trying to figure out why they would do this, and it's because they're missing entity annotation, which they need to evaluate against because this is supervised for the second data set. Okay. We use word-level vocabularies of 9,951 English and 11,216 French words. We use Moses, Cohen et al. 2007, scripts to lowercase, normalize, and tokenize the sentence with hyphen splitting. The hyphens are stitched back prior to evaluation. In my experience, people who are using Moses for preprocessing and normalization are almost always only in machine translation. It seems to be super popular in that particular community. And I don't know why, but it is an NLTK now. So if you're an NLTK person, you can use that. All right, visual features. We use a ResNet 50 CNN, He et al. 2016, trained on ImageNet, Deng et al. 2009, as image encoder. I don't do a lot of computer vision, but I've heard of these models, so I'm guessing that they are very popular. Prior to feature extraction, we center and standardize the image using ImageNet statistics, resize the shortest edge to 256 pixels, and take a center crop of size 256 by 256. So just sort of like using a cookie cutter in the center of each image to get a smaller image that's the correct size to feed into their net. We extract spatial features of size 2048 by 8 by 8 from the final convolutional layer and apply L2 normalization along the depth dimension. I don't know if that's common. Is that usually what you do with the output of a CNN? Yeah, if anyone knows, feel free to hop in. For the non-attentive model, we use 2048 dimensional global average pooled version, pool 5, of the above convolutional features. That's probably what I would do instead of L2. Again, not knowing a lot about computer vision. And so this is the one without attention, and this is the one with attention. Which I believe they're doing both because both have been used previously. So the attention models are these ones by Kaggle et al. 2016. It looks like HELCL, whoever they are, has done a couple of papers on this as well. So I'm guessing that they're using the same architecture from those papers, but I don't know for sure. I guess I could go look, but I do want to finish this paper in an hour, so I'm not gonna get distracted. All right, our baseline NMT is an attentive model, Badnu et al. 2014, which I know we've talked about before in this channel. I think we talked about it when we were reading through the Attention is All You Need paper. I think that's when we went and looked at that. With a 2-layer bidirectional GRU encoder, GRU, et al. 2014, and a 2-layer conditional GRU decoder. So the encoder is 2 layers, the decoder is 2 layers. The second layer of the decoder receives the output of the attention layer as input. Okay, makes sense to me. And I don't think we've seen these, the text for these tables yet, so we'll come back to those. For the MMT model, we explore the basic multimodal attention direct Kaggle et al. 2016 and its hierarchical extension. So sort of flat attention and then hierarchical attention. The former linearly projects the concatenation of textual and visual context vectors to obtain the multimodal context vector, while the latter replaces the concatenation with another attention layer. Okay, so the direct one just sort of squishes everything together and makes like a single sandwich. And this one adds an additional attention layer. So that would be like, I guess like putting the 2 halves of a sandwich on like one of those double-decker tea trays. So you're maintaining the relationship between them. Finally, we also experiment with encoder-decoder initialization, Calixto, and Liu et al., Kaggle et al. 2017. So this person has clearly been pretty, yeah, okay, it's the same as the first author of this paper. So it would make sense that the author is building on previous work. And also, I'm sorry for messing up your name if you were watching this. That is 100% on me. Where we initialize both the encoder and decoder using a nonlinear transformation of pool 5 features. Okay, so instead of random initialization, they are starting their initialization from the pooled features from the visual features? Is that where they're getting pool 5? One sec. Where did you get it from? Okay, yeah. So they're taking the visual features and they're using that to initialize their encoder and decoder. Interesting. I wonder if that works. I mean, they got best paper, so presumably it does. Hyperparameters. The encoder and decoder GRUs have 400 hidden units and are initialized with 0 except for the multimodal init system. All embeddings are 200 dimensional and the decoder embeddings are tied. Aren't you supposed to do random initialization? Isn't 0 initialization bad? Does anyone know off the top of their head? I definitely remember reading something about 0 initialization, and I think it was please don't do it. Feel free to hop in if you know in the chat. All embeddings are 200-dimensional. Oh, that's pretty small. And the decoder embeddings are tied. Okay, so the decoder and encoder embeddings are tied to each other, I'm guessing. A dropout of 0.4 and 0.5 is implied on source embeddings and encoder-decoder outputs, respectively. The weights are decayed by a factor of e to the negative 5. We use Atom with a learning rate of 4e to the negative 4. I know that those are natural logs. I just don't remember how to say them with words. And mini batches of 64 samples. Aren't you also not supposed to use mini batches? I feel like there was a paper recently that was like, mini batches are that bad. That's how I put it in my head. I don't remember if that's actually what the paper said. I'll look it up and tweet it if I remember, and hit me up on Twitter if I haven't. The gradients are clipped if the total norm exceeds 1. The training is early stopped if dead set Meteor does not improve for 10 epochs. All experiments are conducted with NMT PyTorch, so a neural machine translation specific version of PyTorch, it looks like. Okay, so if you guys have comments on that, please let me know. I really thought mini batches were bad. Anyway, let me know. I'll look it up and see what that paper that I remember reading vaguely actually says. Oh, and it looks like there is a link to NMT PyTorch as well. Oh no. Okay. The link is not, the link itself doesn't seem to work. But let me check the text. Sina says, "Hi, I'm Sina from Copenhagen. Hello, welcome." Because if you are working on neural machine translation, I know a lot of folks are a big fan of PyTorch. That's not it. Okay, so this looks like an OCR error. And if I, oh my gosh, go away. Anyway, I will let you guys type that into the search bar on your own. Finally, results. So how good did they do? We train all systems 3 times each with different random initialization in order to perform sentence testing with multi-eval. Didn't it just say they use 0 initialization? For the encoder and decoder. So maybe this is for the image features specifically that they're doing random initialization. In order to perform significance testing with multi-eval. Throughout this section, we always report the mean over 3 runs and the standard deviation of the considered metrics. We decode the translation with a beam size of 12. We first present Test 2017 Meteor scores for the base NMT and NMT systems when trained on the full dataset D, table 2. So it looks like the base NMT system, so everybody's doing worse on the color deprivation system. So when you start to mask words in the source sentence, performance goes down for everybody, which is not super surprising. And it looks like if you are initializing with the weights from the visual features, you are using hierarchical attention, or you're squishing all of the visual features down, those all improve over the baseline. So once you remove the color information, including these visual features does improve performance, and these all look like they don't overlap. So that is probably significant. Yeah, p-values are less than 0.03, which is a weird value to pick, but I guess that's what they did. I'm guessing that it's not actually significant at 0.01 is my guess there. Interesting. So that makes sense to me. So when you remove the color information, then when you rely on the color information from the words, then when you rely on the color information from the images, you get better results. All right, the first column indicates that although MMT models are perform slightly better on average, they are not significantly better than the NMT. We now introduce and discuss the results obtained under the proposed degradation schemes. Please refer to Table 5 and Appendix for qualitative examples. Color deprivation, so that's the one that we looked at up here. Unlike the inconsistent results for D, we observe that all MMT models are significantly better than NMT when color deprivation is applied. If we further focus on the subset of the test set subjected to color deprivation, the gains increase to 1.6. Oh, that's right, because we didn't remove color words from all of the sentences. If we're only looking at sentences that did have color words, then the results improve. That makes sense. I wouldn't expect a difference for sentences without color words that had been masked. For the latter subset, we also computed the average color accuracy per sentence and found that attentive models are 12% better than the NMT, whereas the init models only brings 4% improvement. This shows that more complex MMT models are better at integrating visual information to perform better. So instead of just taking the weights, if you're actually using attention and applying those weights differently to different parts of the image, presumably the parts that are most relevant for your specific task, you get about 3 times better of an improvement than if you're just using the weights to initialize. All right. Oh, and I don't see where that footnote was from. Since entity masking uses Flickr 30K splits, section 3, rather than R splits, the scores are not comparable to those from other experiments in the paper. That's right, because there wasn't entity masking annotations in the 30K dataset, or rather the dataset that they were using, the 2017, I think. Oh, this is entity masking. Let's read the section and then look at the figure. The gains are much more prominent with entity masking, where the degradation occurs at a larger scale. Attentive MMT models show up to 4.2 Meteor improvement over NMT. And Meteor is a metric for machine translation that is better than BLEU, but still not ideal. And I have a big, long blog post on Medium if you really care about machine translation metrics. We observed the largest performance drop with incongruent decoding, suggesting that the visual modality is now much more important than previously demonstrated. A comparison of attention maps produced by the baseline and masked MMT models reveals that the attention weights are more consistent in the latter. Interesting. So when you're masking entity recognition, you're going to get better information from your attention weights in the visual models. An interesting example is given in figure 2, where the masked MMT model attends to the correct image of this correct region of the image and successfully translates a dropped word that was otherwise a spelling mistake. So here we have a so Jun is young, and that is correctly translated in both systems. And then the one that's relying on text translated the word song, which was a spelling mistake. It should have been son, as chanson, which is, French for song. And son, when it was masked, was correctly translated as son, enfant, or image. Sorry, child. And let's go back up and look at the entity masking results. So here we have all masked MMT models are significantly better than the masked NMT. So NMT is neural machine translation. MMT is multimodal machine translation. When we add the visual information, they do much better when the entities are masked. So instead of no information, you have a picture with some information that you've gotten from it using your technique, whatever that is. Incongruent decoding severely worsens all systems. So this is when the image information is not the same as the text information. The vanilla NMT baseline is 75.9, which I don't think is right. They say that it's 50.5 here. So I'm wondering if that is oh no, that's what they were saying, that they can't directly compare them to each other because of the differences in annotations between the two. Okay, that makes sense. So it looks like the direct model, which is like the sandwich that's squished together, does better than the hierarchical model, which is the sandwich broken apart. Sina says, is it image processing or text processing? So it's both. And the question that the paper is asking is, if you're doing machine translation and you have an image, is the image actually helpful? And previous results have suggested that it's not. And this paper suggests that it is in instances where the text information for the language that you're translating from has been removed or reduced in some way. So, good question. I want to do a little bit of image processing because I don't generally do a lot of that. Blah, 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 blah. And then when you have the wrong image information, things are always much worse than when you have the correct image information. All right. And then entity masking results across 3 languages. Oh, incongruence should be down and gain should be up. And these all have lower incongruence between the different languages. The incongruence drop applies on top of the MMT score. Okay, so presumably they're going to talk about the Czech and the German down here. And then I don't think we've talked about figure 3 yet. Oh, that's the progressive masking. Yeah, we definitely haven't talked about the progressive masking yet. Czech and German. In order to understand whether the above observations are also consistent across different languages, we extend the entity masking experiments to German and Czech parts of multi-30K. So they're translating from Czech to German. I don't think Czech is Germanic, so that is a fairly hard translation pair. Table 3 shows the gain of each MMT system with respect to the NMT model and the subsequent drop caused by incongruent decoding. And basically, in all instances, adding information helps if you are masking entities, adding visual information. First, we see the multimodal benefits clearly hold for German and Czech, although the gains are lower than for French. Second, when we compute the average drop from using incongruent images across all languages, we see how conservative the init system is compared to the hierarchical and direct. So adding attention gets you a much bigger drop in drop in incongruence and gain in performance. And I think this is specifically Meteor. So the numbers are bigger in the hierarchical and direct sets than they are in the init sets, is what you should get from this figure. This raises a follow-up question as to whether the hidden state initialization eventually loses its impact throughout the recurrence, where, as a consequence, the only modality processed is the text. So they're suggesting that the initialization eventually doesn't have any effect as your model trains, and those weights that you started with are updated. All right, section 4.3, progressive masking. I'm gonna take a quick sip of coffee. Okay. Finally, we discussed the results of the progressive masking experiments for French. Figure 3 clearly shows that as the systems are progressively degraded, so you remove words from the end, all MMT systems are able to leverage the visual modality. At the dashed red line, where the multimodal task becomes image captioning, so when you've removed all of the source sentence, MMT models improve over the language model counterpoint by around 7 Meteor. So when you remove all the language information, images are helpful, is what they're saying in that section. That makes sense? Further qualitative examples show that the systems perform surprisingly well by producing visually plausible sentences. See Table 5 and Appendix. To get a sense of the visual sensitivity, we pick the direct model trained on 4 degraded variants and perform incongruent decoding. So this is when the visual information and the text information don't match. We notice that the amount of linguistic information, as the amount of linguistic information increases, the gap narrows down. The MMT system becomes less perplexed by the incongruence, or put in other words, less sensitive to the visual modality. So the more language there is, the less helpful the visual information is. And that's what this line shows, and they sort of cross over here when you get to very few words removed. To get a sense of visual sensitivity, oh, wait, we already read that. Moving down. So here are some examples. So the reference is, oh, I'm going to have to bust out my French, which is a little bit rusty. Une femme âgée en bikini bronze sur un rocher au bord de l'océan. So a older woman in a bikini tans on a rock at the edge of the ocean. And the source was an older woman in, and then the rest was ablated. And the neural machine translation says an older woman in a white t-shirt. She is not wearing a white t-shirt. And sunglasses. She's not wearing sunglasses. Is sitting on a bank, which is not the case. I guess kind of it's the bank, but it's sort of the edge of the ocean and not a river. And then the multimodal machine translation, which is also taking features from the image, says an older woman in a pink swimsuit. So remember that if we're using global features, we have color as well, is sitting on the side of the ocean, is sitting on a rock on the side of the ocean, which she is doing. So if you just give a machine translation half of a sentence and ask it to keep going, it will sort of hallucinate some things. And if you also give it a picture, it will say what's in the picture. I don't think this is a surprising result, but it is kind of cool. And here we have an example of a woman, and she's in white, and she's holding a tennis racket. And in the source, they've masked the entity. And the neural machine translation has said a young boy in blue holding a tennis racket, none of which are correct. And in the, so in French, articles need to agree in gender with the noun that they are headed by. So in this case, jeune femme, a young woman, would have une, and garçon, boy, would have un. A little brushing off my college level French there. And if you have the image with the multimodal machine translation, we get the correct output out and not this hallucinated output, which I don't know why you would expect just a neural machine translation to get the correct output out if it didn't have didn't have access to the information in the feature. And then finally, this is the color masking. So it's a blue towel. The hallucinated example, just plain neural machine translation, is white. I guess a lot of towels tend to be white in their training corpus, but in actuality, it's blue. And when you add the visual information, you get blue out. So I don't think that these results are especially surprising, but it is nice to see some examples. Here we see. So continuing, we then conduct a contrastive blinding experiment where the direct models are not only fed with incongruent features at decoding time, but also trained with them from scratch. So training the model on visual features from images that aren't described by the captions they're attempting to translate. The results suggest that the blinded models learn to ignore the visual modality. That makes sense because it's not informative. In fact, their performance is equivalent to NMT models, but you spent more time and energy and compute training them. So I don't know why you do that. So there's a good takeaway from this paper. Don't train multimodal machine translation models on image features taken from images that they're not describing, which I don't think anyone would have done to begin with. But it is, it's always good to have empirical verification of that. Discussion and conclusions. We presented an in-depth study on the potential contribution of images for multimodal machine translation. Specifically, we analyzed the behavior of state-of-the-art MMT models under several degradation schemes in the multi-30K dataset in order to reveal and understand the impact of textual predominance. Our results showed that the models explored are able to integrate the visual modality if the available modalities are complementary rather than redundant. So if you're getting additional information from the image features, then it's good to include them. If you're getting all the information you need from the source text, don't bother. It's just time and money and energy you could spend on something else. And also probably tends to make inference time a little bit slower would be my guess. The dominance effects corroborates the seminal work of Colavita in psychophysics, where it has been demonstrated that visual stimuli dominate over the auditory stimuli when humans are asked to perform simple audio-visual discrimination tasks. Interesting. I'm not super familiar with this work. It is a little bit old. Interesting. So there's something sort of similar to this in linguistics called the McGurk effect. And the McGurk effect is when you have an image of somebody saying a sound, and you also have a recording of somebody saying it, and they don't match. So you might be saying tuh, but have an image of somebody saying buh, or sorry, you might have audio of someone saying guh as in gate, but saying buh as in butcher. And then what people usually hear is something between those two sounds. So more like duh as in Denmark. So I don't necessarily know that auditory stimuli are always dominated by visual stimuli, especially for language processing in particular. But we definitely do use visual stimuli in language perception. Our investigation using source degradation also suggests that visual grounding can increase the robustness of machine translation systems by mitigating input noise, such as errors in the source text. So that I definitely agree. They have this nice example where there's actually a typo in the source text, and neural machine translation translates the typo, and with visual information included, the typo is ignored, and then the correct output is given. So I definitely agree that if you have especially noisy captions, this might be a really nice technique. In the future, we would like to devise models that can learn when and how to integrate multiple modalities by taking care of the complementary and redundant aspects of them in an intelligent way. So sort of the direction for future work is to figure out when to use visual information and when to use when to use textual information, and how to balance those types of features. And then there's some acknowledgements that I'm not going to read, but you guys are welcome to. And I think they said there was some additional stuff in the appendixes. So in our last 10 minutes, let's go through these examples. And we finished the paper in an hour, which I am super proud of. And just before we go through some examples, sort of my main takeaways from here are, if you are doing image captioning and you have high quality captions, don't bother working with the images. It's just going to take longer and it doesn't look like it actually gains you a lot. But if you're working with image captioning or translation and you have low quality, so this is specifically for an instance where you want to translate image captions. So if you're working with image caption translation and you have low quality annotations and captions in your source language, then including visual information might be helpful. I don't know how realistic the specific task they had of the, what do they call it? Progressively chopping things off the end of the sentence was. Progressive masking. That's kind of a weird thing. I guess I don't know a whole lot about situations where you would be building a system for multimodal machine translation, but it seems weird to have a situation where you'd only get the first half of a sentence. At least in sort of conversational speech, just talking to people, you tend to miss specific words in a sentence rather than half of it, unless like someone starts a jackhammer. So I don't know about how well the results from the progressive masking in particular are going to transfer to other examples, but something to think about. All right, let's look at a couple of examples. So in our example, the fact that the girl is wearing black is masked, and only the hierarchical and direct, so the image models with attention correctly get that it is black. Here, the man is dressed in white. So even the system that is initialized with the weights from the CNN is still incorrectly saying that this man is wearing black. Whereas the hierarchical and direct models, which include the attention, correctly identify that it's white. And it looks like just a lot of examples like that. And it looks like they're sort of showing that the direct model, so this is where you don't maintain the hierarchical nature of the attention, seems to be performing slightly better than the hierarchical model, which is sort of interesting. And then here we have some entity masking. And again, the neural machine translation model is literally just hallucinating things. It's just coming up with things that aren't the thing that it is, which is completely surprising since it doesn't have information it doesn't have information about what's in the image. And this is more like a language modeling sort of BERT thing where you're replacing the missing words. And these are all just sort of the same examples. And then here it's interesting. So here they're showing that the baseline model does not have more attention on the boy for the word. Sorry, it's this image. It does not have more attention for the boy, but the model with attention is correctly with the masking. No, sorry, it's not masked, but it does have. No, this one is masked. This one is not masked. Sorry. So this label goes with the image above, and this label goes with the image above. So when there is masking, there is more weight placed on attention at different parts of the image. So there's more use of the image than there is when the entities are not masked and there are just words that are available that are the words that you're trying to translate. And it looks like the same thing as well. And then some ablation examples where, again, the neural machine translation models are just sort of hallucinating as the text that they're using is reduced over time. All right, so interesting paper. I think it does sort of help to provide additional information on this finding from a number of different people that the images actually aren't helping. And it looks like the reason that the images aren't helping is because there's so much information in the language, in the source language that you're trying to translate from. So I'm going to wrap it up here. It's almost lunchtime, and I know that people want to go get food, and by people also I mean me. I want to go get food. I will hopefully be back on Friday for live coding. If my flight is delayed, that won't happen because I'm cutting it pretty close. But if that does happen, I will mention it on the YouTube channel, and also I'll tweet about it so you guys know and you're not like, where's Rachel? And then next week, just a little plug, reminder that we won't be doing the reading group because I will be doing the live streaming for the CareerCon event. We're going to be building an API from scratch. And if you've never built an API before and you don't even really know what an API is, that's absolutely okay. We're going to be starting from absolute nothing. I'm not assuming you're a software engineer. I just want you guys to have these skills and develop them and have a chance to play around with building APIs. And of course, there's also lots of other great CareerCon content. I'm giving a talk with Suraj on sort of how to social media and some best practices for growing and developing a community online. And then next Friday, I should be back with more live coding, and I will keep you guys updated. And if anyone's going to PyCon, I'm going to be at PyCon. I'm giving a talk. So if you're there, I will hopefully see you there. All right. Thanks for joining me, everybody. I hope you found this helpful and interesting. I always like to keep an eye on the best papers because they tend to be things that the research community thinks are going to be very influential. And this was definitely an interesting paper, and I feel like I have a much better idea of the state of the art in multimodal machine translation right now. And if I wanted to build a system, I would know how to do it. All right. You guys have a great day, and I will talk to you on Friday, maybe. Bye-bye.